Okay. Hello guys. Welcome to the lesson of DBA from Introduction to Practice. I'm your old friend Peng Wang, the Global Technical Evangelist for OceanBase. Today's lesson is the second part of diagnosis and tuning of OceanBase. Let's get started. And today's lesson consists of two parts: common SQL tuning methods and troubleshooting SQL performance issues. Let's dive into the first part, common SQL tuning methods. Let's first introduce the background knowledge, statistical information. For example, in the SQL line, two tables R1 and R2 are joined. There may be multiple methods to complete this calculation, such as nested loop join, Hershey join, and other paths such as sort merge join. The optimizer uses the cost module to estimate the cost of different paths based on the stats information of the two tables. Here, we can see the importance of statistical information for the optimizer. It helps to estimate the size of intermediate result set and provides insights into data distribution patterns. This information enables the optimizer to make better decisions regarding index selection, joining methods, sorting strategies, and others. Stats are a collection of information describing database objects such as tables, indexes, and columns in the database. It can be divided into the following three categories. The first category is table level stats, which includes the number of rows, mini and max blocks, which can be used to estimate the cost of I/O, and the average row length, which can be used to estimate the cost of network transmission. The second category is column level stats, which includes the number of distinct values in the column, commonly referred to as NDV. These stats are used to estimate the number of result rows after applying equality predicates or filtering conditions based on exact matches. The last category is index stats, which is similar to the main table, and I want to introduce more here. To implement a histogram, the progress involves dividing the value range of a column into several buckets, with each bucket containing a subset of columns values, and the frequency of data within each bucket is then recorded. We support multiple types of histograms. During the collection of stats information, the optimizer selects the most suitable histogram based on the column's data distribution. Regardless of the histogram type, accuracy improves with an increased numbers of buckets. By default, a histogram contains 254 buckets. However, while a higher bucket count enhances the accuracy of the stats information, it also increases the cost of the collecting stats. OceanBase version 4 currently supports three stats information collection methods. They are manual, automatic, and online collection. Manual collection means the user actively initiates the collection and some customized collection can be done. And automatic collection means The background thread automatically triggered the stats information collection task. And online collection means collecting stats information while inserting data. We provide two ways to manually collect stats. One is DBMS stats system package, and the other is the analysis command. We recommend you to use the DBMS stats system package to collect stats because it supports more functions. And there are many parameters in the stored procedure of this system package. Just look at the examples, and you will know how to collect customized stats by changing these parameters. In the first example, it's supplied to collect stats for the entire table T1, and the number of buckets is set to 128. In the second example, partition level stats for table T part 1 are collected. This means stats are gathered as the granularity of each partition, rather than for the entire table. Additionally, stats are collected only for columns with uneven data distribution to capture the most relevant patterns. In the third example, all stats of table T sub part 1 are collected, but only 50% of the data is collected. And in the last example, the stats of all tables in the test library are collected. In order to improve the collection efficiency, the parallelism is set to 128. In addition to manual collection, the OceanBase database optimizer also uses a maintenance window to automatically collect stats daily. This ensures that stats information remains up to date without requiring a manual intervention. The OceanBase optimizer defines 7 automatic stats collection tasks from Monday to Sunday. OceanBase provides two system wheels, scheduler window and scheduler jobs, which can be used to query the execution status of automatic stats collection. These two wheels shows the collection tasks that are executed regularly, their last execution time, and when they are expected to run next. Considering that some users may need to modify some attributes related to automatic stats collection according to their business characteristics, an OceanBase optimizer provides a summary method to modify various attributes of automatic stats. For example, we can use scheduler disable to disable the collection task for 13 days, and use scheduler stat attribute to set the start time of the collection task on Monday and the duration of each collection. Here is the working mechanism of automatic stats. OceanBase determines whether a table's stats are out of date, mainly based on the proportion of data changes since the last stats collection. The default value is 10%. In other words, if the change rate of the table exceeds 10%, the system considers the status of the table to be out of date and needs to collect stats again. It should be noted that if the corresponding table is partitioned, the change ratio is at the partition level. For example, if the change ratio in certain partitions of a partitioned table exceed 10%, the stats of those partitions will be automatically recalculated and updated. When you have collected stats information or want to confirm whether a table has stats information, OceanBase also provides a very rich way for querying the collection status of various stats information. And you can review this part after this lesson or refer to the OceanBase official website. Let's look at an example of using wheels. Create a partition table 𝘤𝘠 Insert 1000 rows of data, all with the value of 1. Query the table level stats of 𝘤𝘠. Since stats have not been collected yet, or you can say are none, use the analyze command to collect stats for this table. Query the table level stats of 𝘤𝘠 again, and you will notice that the first row represents the table itself, while the following rows represent individual partitions. The entire table has 1000 rows, all concentrated in partition P1, with an average row length of 20 bytes. The last column shows the timestamp of the last stats collection. Overall, the system wheels related to the stats provide clear and easy to understand information. After collecting the stats, let's do another query. Since the C1 column of the table contains only the value 1, the filter condition will exclude very few rows, resulting in a minimal reduction in the number of rows. In the plan, we can see that the estimated number of rows of the filtered data is only 1, which is very close to the actual number of rows, which aligns with expectations. Let's insert 1000 rows of data with the value of 99 into this table. Let's execute the SQL again, and we can find that for the same filter condition, the estimated number of rows is still very small, which should be 1000 rows, right? But it shows only 1 row, which doesn't align with expectations. The reason is that the optimizer has not collected stats in time. After manually collecting stats, you can see that the estimated number of rows in the plan is in line with expectations. When executing SQL, you can, if you notice that the execution plan is not optimal, check whether stats collection are triggered after significant changes to the data. If the system hasn't automatically updated the stats in time, you can collect them manually. This will likely result in the generation of a better execution plan. Next, we will introduce the index tuning. That is, how to create a suitable index in OceanBase. Let's talk about some background knowledge first. In addition to the index key specified when creating the index, the OceanBase index also contains the primary key of the main table. Let's do a simple experiment. Create a table test. create a primary key on column A, and create an index called IDXB on column B. And then, let's check the columns of this index table. In the meta information table, you can see that there are two rows. One is A, and the other is B. The index position of B is not 0, which means that the column B is an index column explicitly written by the user. The index of position of A is 0, which means that is the primary key column added to the index by OceanBase. All OceanBase tables currently have primary keys. If a table without a primary key, OceanBase will automatically create a hidden auto-increment column called PK, and then create a hidden primary key on this auto-increment column. Therefore, when creating an index on a table without a primary key, the index will include this hidden primary key column. Here is the schematic diagram of the index back to the table, which can more clearly show when an index back to the table is needed. Let's look at the picture on the right. There are two columns in a table, C1 and C2, and then I create an index on the C1 column. If there are many columns to be queried, such as selecting C1 and C2, you need to get the value of column C1 obtained from the index and the corresponding rows of these values in the main table. Return to the main table to query the value of column C2 in the corresponding row, and finally piece together the result side of C1 and C2. This is called index back to the table. If the C code only selects C1, it's sufficient to use the index table directly without scanning the main table. Please note, the cost of retrieving data from an index table is significantly high. Typically, the performance of an index table retrieval is only about 1/10 of that of a direct full table scan. Additionally, global index table retrieval incurs extra cost due to the network transmission, making it even less efficient compared to local index table retrieval. The second background knowledge is the role of indexes. When querying, use the indexes has three advantages over using the main table. They are reducing row rates, eliminating sorting, and saving I/O. The first advantage of an index is that it can quickly locate data and reduce the amount of data scanned. This is because the filter condition on the index column can be converted into the start and the end position of an index scan. When scanning, you only need to scan from the start to the end position, and there is no need to scan the entire table. The data between the two positions is the data that meets the filter conditions on the index column. The start to the end position of the index scan is called the query range in OceanBase. Let's take a simple example. In the test table, column A is the primary key column, and then create an index IDXBC on the column B and C. We insert a batch of data and then select all of them. We can see that the data in the main table is ordered according to the primary key, column A. However, if a hint is used to force select all to go through the index table, you can see that the data on the index is ordered according to columns B and C. In fact, it's ordered according to 3 columns, B, C, and A. Next, execute a few SQL statements to say when the SQL can use this index. The following SQL statement has a filter condition of B equal to 1. And the corresponding query range is like this. We need to start the vector point B equal to 1. C is meaning, A is meaning, and scan all the way to the vector point B equal to 1, and C is max, and A is max. Because all the data between these 2 vector points satisfy the B equal to 1 condition. We only need to return this batch of data after scanning, and no additional filtering is required. So the filter in the plan is empty. The following SQL statement has a filter condition of B larger than 1. The scan range of column B in the query range is changed from 1 to 1 max. The filtering condition of the following SQL statement are B equal to 1, C larger than 1. The corresponding query range is like this. The first predicate is the condition B equal to 1, and the index will continue to match backward until the first range condition C larger than 1 appears. The following SQL statement has filtering condition of B larger than 1 and C larger than 1. When the query range is extracted on the index, only the first range predicate can be extracted. In this case, with conditions B larger than 1 and C larger than 1, the first column of the index is used as a range predicate. As a result, subsequent equality or range conditions cannot contribute to defining the range. In the plan, you can see that the index back is true, which means that the index needs to return to the table. After the index is returned to the table, it's necessary to filter C larger than 1 again. Therefore, when creating an index, you should put the columns that often appears in equal value conditions at the front of the index, and the columns that often appear in range conditions at the back of the index. The first function of the index is to quickly locate data as just mentioned. Because the index itself is ordered, the second function of the index is to use this ordered feature to eliminate the overhead of sorting. Here are a few simple examples. First, create a table named test. Create a primary key on column A, and create indexes on columns B, C, and D. This SQL statement uses the index IDX B, C, D. In the plan, we can see that there is only a table scan operator but no sort operator, which means that column C doesn't need to be sorted after the index is returned to the table. This is because the index is ordered by B, C, D, and E. But in the scan result, B is always 1, so the return data is ordered by C, D, and A. Therefore, ordered by C doesn't need to sort it by the sort operator. Note that the index back is false, which means after the index scan is completed, there is no need to go back to the table, and the results can be output directly when the index already contains all the columns being queried. You can also reduce the overhead of index back to the table by creating such an index that covers more columns. This SQL statement needs to be sorted. There is an extra OR here. The plan will scan 2 batches of data through the index, although column C is ordered within the 2 batch of data. It's out of order between the two, but it's out of order between the 2 batches of data. Therefore, a sort operator will be allocated on the upper layer of the table scan to sort the column C. This SQL statement is similar to the first one and doesn't require sorting. In the following SQL, C is a constant and the index is ordered by B, C, D, and A. Therefore, if you want to sort by B and D, you can directly query the index table using the filter condition C equal to 1. When index back is set to false in the execution plan, it means that the filter condition is applied directly to the index. After applying the filter, while the returned data may be discrete, and the data within each batch and between batches remains ordered. As a result, no additional sorting is required, and the sort operator will not be included in the execution plan. The third function of the index is that when querying a satisfied column, less data can be scanned compared to the main table. For example, in this SQL, an index is created on column B, and then SQL is executed to select the data in column B. The plan shows that the data will be directly found on the index IDXB. If the data is found on the main table, the data of the redundant column A, C, and D need to be scanned, and the optimizer will not choose to do this. For example, the following SQL statement calculates an aggregate count. In this scenario, the optimizer will also select the index IDXB with the least number of columns for scanning. There is also a disadvantage here, that is, if there are many columns to query. If the index is used, it's necessary to index back to the table, and the cost of index to the table is very high. As mentioned earlier, the performance of index back to the table is generally only 1/10 of that of directly scanning the entire table. Let's look at the SQL statement. The index is built on B. The values of column A and B are queried. If the entire table is scanned directly without using the index, the optimizer estimates that the cost is 2 microseconds. If you force the use of index specifying a hint, the optimizer estimates the cost time to be 5 microseconds, which is slower than not using the index. This is the extra overhead caused by the index back to the table. Here is an introduction to measuring the time it takes to index. The time spent on index consists of 2 parts. The part to scan the index, and the second one is the time to return the index to the table. We create a table test. Column A is the primary key column, and the index is built on the 3 columns B, E, and C. Assume that this table has 10,000 rows of data. The time to scan the index is 1 millisecond for 1,000 rows, and the time to index back to the table is 1 millisecond for 100 rows. If we execute these SQL statements, use the index, the overhead is scanning 1,000 rows of data on the index, which is about 1 millisecond. If without the index, the cost is scanning 10,000 rows of data in the main table, which takes about 10 milliseconds. So in this scenario, it's faster to use the index, right? If the generated plan doesn't use the index, you can specify a hint to force it to use the index. If we change to select A, B, C to select star, it means select all. We need to index back to the table because there is no data in column D on the index. At this time, the cost of using the index is scanning 1,000 rows of data on the index, and indexing back to the table 1,000 rows of data, which about 1 millisecond plus 10 milliseconds is 11 milliseconds. The cost of not using the index is that scanning 10,000 rows of data on the main table, which takes about 10 milliseconds. In this scenario, it's faster to use the main table instead of the index. If the generated plan uses the index, you can specify a hint to force it to use the main table. We have a question. How to get information like filtering with B equal to 1 and C equal to 1 will return 1,000 rows of data? Very simple. Just execute this SQL statement and check the count. Finally, let's summarize the strategy for creating indexes. 1. Put columns with equal values conditions at the front of the index, and the columns with range conditions at the back of the index. When there are range conditions on the multiple columns, put the columns with strong filtering properties at the front. And the last one is using common covering indexes. You can effectively avoid back to the table. For example, there are 3 filtering conditions in a SQL statement. They are A equal to 1, B larger than 0, and C between 1 and 12. The condition B larger than 1 can filter out 30% of the data, and the condition C between 1 and 12 can filter out 90% of the data. So, how should we build an index? According to our basic strategy, for this SQL statement, you can create an index on A, C, B for optimization. A is in the front because A is an equal condition. C is after A because C is a better filter than B in range query. C is added at the end because if the query projection columns contains B, and the overhead of indexing back to the table can be eliminated. When we found that a SQL statement has performance problems, we can optimize it in many ways. The most common of which is index tuning. Index tuning is a relatively simple tuning method, and it's also the optimization method that is usually considered first when SQL statement has performance problems. So today's lesson, we know that if we want to improve query performance through indexes, we should build indexes on which columns, how to arrange the order of index columns, and others. Among the contents related to the SQL performance tuning, users need to master three main parts: index tuning, connecting tuning, sorting, and limited tuning. You can also visit the official website of OceanBase and join our community, which has a lot of content for your reference. The last part is the troubleshooting idea for SQL performance issues. Okay, let's move on. When users encounter performance problems caused by SQL, they can generally troubleshoot through the following steps. The first one, use full link tracking to confirm the time consumption ratio at each stage, and identify which stage takes the longest time. If it's slow in the OB server module, you can use SQL audit to analyze which stage in the OB server is the longest. If it's slow in the execution stage, you can first determine whether there are problems such as buffer tables, big and small accounts, and parsing problems based on the above content. If there are no issues above, use explain extended to check if there is a big gap between the optimizer estimated and the actual row count. If so, collect the stats manually. Otherwise, consider adjusting the index, execution plan, or parallelism with hints. Next, we will show you several tools mentioned in the above troubleshooting steps that are commonly used to analyze SQL performance issues. Before introducing typical scenarios of SQL performance problems, let's first briefly introduce a common chord show trace, which can be used to track the entire link of the SQL execution. When end-to-end performance problems occur, at this time, we first need to locate which component on the entire database link has the problem, and then we can troubleshoot the specific problems in the component. Full link tracking covers two main data flow paths. One is forwarded to the OB server through the proxy. The other is directly connected to the OB server. Next, let's use these two paths to give a simple example. First, connect with an ODP and enable full link diagnostics for the current session. Then, execute a simple query followed by the 𝘂𝘁trace statement. From the 𝘂𝘁trace result, you can analyze some information. And the 𝘂𝘁 token took about 191 milliseconds in total. The overall cycle time consumption is mainly in OB proxy partition location lookup, which takes 181 milliseconds. As the name suggests, the part of the time consumption in the ODP looking for the location information of the primary copy of table T1. However, because this table has just been created, there is no corresponding location information cache in ODP yet. So, it will take a long time for the first time. However, after the first time, ODP will catch the location information of this table. After the SQL is forwarded to the appropriate OB server node, the time spent in common query process is very small, only 8 milliseconds. Let's execute the SQL statement again in the same session and see if the 𝘂𝘁trace changes. From the above 𝘂𝘁trace result, you can analyze some information. The first time of the SQL statement was executed, the execution time was much faster, from 191 milliseconds to only 7 milliseconds. Because ODP has the location cache information. So searching for routing information and forwarding is faster, from 181 milliseconds to only 4 milliseconds. After this SQL is forwarded to appropriate OB server node, the time consumed in common query process is reduced from 8 milliseconds to 1 millisecond. Next, let's use the second part to connect directly to an OB server to say what changes are made in the 𝘂𝘁trace. From the above 𝘂𝘁trace results, you can analyze some information. When connecting directly to the OceanBase to the OB server, there is no ODP, so there is no proxy-related overhead. Finally, let's briefly summarize. For SQL whose performance doesn't meet expectations, full link tracking can be used to say at what stage the time is spent. Each stage also provides more detailed in-time information, allowing us to further analyze the specific bottlenecks. The next SQL performance analysis tool is SQL Audit. SQL Audit is the performance wheel, which has been mentioned in the previous introduction of SQL monitoring wheels. So I will not introduce it here again. And next, I will introduce several typical scenarios of SQL performance issue. The first one is the buffer table scenario. The problem with buffer table is that OceanBase uses a storage engine based on LSM tree. In the LSM tree architecture, deleted data is marked as such and remains effective until a merge occurs. Here is an example. Insert 1000 rows of data, and then delete every other rows. When scanning the table again, the plan indicates only 500 logical rows need to be scanned. However, because the LSB tree marks deleted rows in the memory without merging them, 1000 physical rows are still scanned. In addition to viewing this plan, after the SQL is executed, you can also use the SQL audit to view the physical and logical rows of the corresponding SQL. We can manually initiate a merge. After the merge is completed, the data previously marked as delete will be deleted. And then execute the explain command to say both the physical rows and the logical rows are all 500 rows. The typical scenario of SQL performance problem introduced below is the big and small count problems. This problem is a bad case of plan catching. We mentioned earlier that for parameterized SQL, after the execution plan is generated, the plan will be saved in the plan cache, and subsequent SQL execution will hit this execution plan. Although this plan reuse method can save time in generating plan, it implies a bad case in a special scenario. Here we take an example. Let's create a table T1, and the one column contains only two values, 1 and 0, with counts of 999 and only 1. And the C2 column has 10 values from 1 to 10, each accounting for 10%. Then manually collect the status of this table. Execute this SQL. Then the generated plan will be cached in the plan cache, because the filter condition C1 equal to 0 is very effective. You can see in the outline data that the cached plan uses IDX1, which is the index built on the C1 column. Execute this SQL. The filter condition C1 equal to 1 in this SQL statement is much worse than C1 equal to 0 in the previous statement, because most of the data in column C1 in the table is 1. However, the result of this parameterized SQL statement is the same as the previous one, so the plan just generated will be reused. However, it's obviously not appropriate to use the IDX1 index on the C1 column at this time. The index on the C2 column is the best choice. This scenario is the bad case for plan catch. We usually call this problems the big and the small account problem. Of course, there are many ways to solve this problem. For example, you can use the hint we just introduced to specify that the SQL uses a specific index. You can also use the command out system flush plan cache we introduced earlier to clear the plan cache of the specified plan. Another method is to make a slight change to the parameterized result so that it cannot reuse the plain catch. Here is an example of changing the execution plan. By adding a space in the middle of C1 equal to 1, the parameterized result changes, and the index used in the generated plan also changes. So one thing to note here is that space need to be added in the middle of the SQL statement, and cannot be added at the beginning or end. Another common performance problem is that the space allocated to the plain catch is too small, which causes plans in the plain catch to be frequently eliminated. Each time a plan is generated, a completed parsing process must be performed. If you encounter this problem frequently, you can increase the OB plain catch persistence system variable appropriately. For example, change from the default 5% to 10%. Another scenarios such as capacity issues and internal weighting issues will not be explained in this lesson, and you can go to the OceanBase official website, or you can join our Slack or GitHub community for help. Okay, so if you have any questions, now is the perfect time to ask. Let me check the QA channel. Okay. Before we wrap up, I'd like to remind you that our next lesson will be next Thursday evening, where we will be covering how to use diagnostic tools to diagnose and tuning OceanBase. We look forward to seeing you then. And you can also reach out anytime through our OceanBase GitHub and Slack community for further assistance. We are always here to help. We will be sharing how you can access the course materials and today's presentation slides in the comments section of this video. All the resources are free. Don't forget to subscribe to our OceanBase YouTube channel and join our community to stay up to date and get involved with us. See you guys. Bye-bye.